we have looked at Exploratory Data Analysis Part 1, where we discuss missing data and data transformation. This second part, we want to look at data types and data distribution. All right, so let's go ahead. We need to look at what type of data do we have and how our data is normally distributed before we go into practical section. Type of data. We have types of data we deal with in data science. All right, we have categorical or qualitative data, and we have numerical or quantitative data. The categorical data based on descriptive information. For example, you can say E is a clever boy. Okay, this is based on descriptive, right? Very descriptive in nature. Under that, we could have a nominal or ordinal. The word nominal means that the data is not ordered, right? Variable data which is in unordered form, for example, red, green, male, female, they are not in order form. Red, green can be color as a variable color. So red, green, blue, and the rest. Man or male can be gender, male, female. They are not ordered. All right, they are different from ordinal. They are both categorical, but the one is nominal, while another one is ordinal. Ordinal are variable data that wish with a proper order, e.g., short, medium, long. So one comes before the other. So there is an order in this case. All right. For example, you can have educational level. For example, we have a high school, bachelor's, master's, PhD. This is ordinal. Okay, it has a proper order. Or you have rating, for example, as a column. You have a poor, you have fair, you have good, you have excellent. Or you can have a Likert data. Maybe you can have a strongly agreed, not agreed, neutral, and the rest of them. So that is a ordinal data. All right. So we have them in various form. All right, but it is obvious you by looking at the data, this one is ordinal, this one is nominal by the way they are ordered and or the way they are unordered. Simple. So that is under categorical data. But under numeric data, we have data based on numerical information. E.g., it has two legs. Two indicate that the number is countable. It's numerically ordered. Quantitatively in a good arrangement. So we have numbers mentioned here. It can be discrete. It can be continuous. Discrete is countable. Number of children, whole numbers. All right. So we can also have something like a number of cars in a parking lot, rolling of a six size of die, number of students in the class, score of a student in a class, score of a student in a test, understand, and so on. So that's just example of a discrete data. They are not continuous. They are basically discrete, right? But we also have continuous. This is the measurable data, e.g., height, width, length, right, or temperature. They are continuous. They have measurement. Temperature is in degrees centigrade, right? Or so in Celsius rather. So we have continuous. They are measurable data. Okay. Sometimes some people even categorize them into ratio and interval sometimes. So, but let's leave that for now. Okay, let's just agree and then look at this. But those ones are called metrics data. Metrics. So we categorize them in form of metrics instead of using discrete data and continuous data. Can call it metrics. But don't let us use that language. Let us just focus on discrete and continuous so that you can understand what we are doing when we see the data later. Be able to differentiate between both of them. All right, so that is the structure of our data set. This is common data that we deal with in data analysis. Common data. The data will fall into several categories of this. Whether it is nominal, it is ordinal, it is discrete, it is continuous. It will fall into category of one of these. Okay. So just take note of that. So when we see the data later, we will now be able to understand where does it fall into. We need to understand better our data analysis. Okay, so let's go. We have what they call test for normality, which is one of them is called skewness. Our data that we are talking about, is it normally distributed? Is it in a proper distribution? So skewness is a statistical measure that assesses the asymmetry of a probability distribution. It quantifies the extent to which the data is skewed or shifted to one side. From what you are seeing here, you can see this is skewed to the left, this is skewed to the right, this is normal. All right, so the data should be like this. Okay, this is Gaussian. This is called Gaussian distribution. That's what I'm talking about the other time, called Gaussian distribution. Okay, that's how it would look like. Whenever it is turned like this, it means it is skewed left. This one is skewed like right. So this was negative, positive skew. It's negative skew. All right. So for example, now we have a negative skew. Look at how it look like. In negative skew, we more points on the right side and tail leading to the left side. We have more points on the right side here, more points here. Okay, we have more points here, right side here, and the tail leading to the left here, left side. And skewness value is less than 0. The value, when you calculate the skewness value, is less than 0. Outliers are present on the left side of the graph. Outliers are present. Okay, that is what it means. That's why it is skewed to the left, right? Median is greater than mean. Median, as it is median, okay, the value of median is now greater than mean, as it's greater than mean. So it is called negative skew or left tail. All right, so we also have what they call positive skew or right tail. Because the tail is on the right side. Okay, so this means more points on the left side and tail leading to the right side. Skewness value is greater than 0 at this point. Okay, outliers are present on the right side of the graph. This one, outliers present on the right side here, and the mean is now greater than median. All right, so you can see the mean, this mean now, this median. So mean is greater than median rather. Mean is greater than median now. Okay, but the former one, we have median greater than mean. You can see that this is a for negative skew. That's the difference now. So you should take note of that. We will see that practically later as we continue in our analysis. So this is called symmetrical. This is normal distribution, right? This is how your data should be or close to this. It may not be exactly like this actually. Normal data in reality is not always like this. Okay, don't be dismayed when you see your data not exactly like this. Normal data in reality not always like this, but you can make it close to this, not exactly, but close to. The purpose of normality testing is to make data close to normal distribution, not to make it normal, to make it close to normal. All right. So skewness value becomes 0, no outliers, mean equal to median equal to 0. So that is here they both lie on the same plane, on the same axis, on the same plane, on the same line. So that is called mean becomes median. So and it becomes mean becomes 0. So 50-50 this side, 50 this side. So that is called symmetrical. It's symmetrical. So that is called test for normality using skewness. So this what you are seeing here is skewness of this is skewness of the data. Skewness. Data is skewed. So either skewed to the left or to the right or symmetrical. The skewness of this one is symmetrical. Okay, it's not asymmetric. So you must understand that. So when you see data like this, you know this one is skewed. I mean this one is symmetrical, not skewed left or right. All right. We also have what they call kurtosis. In statistics probability theory, researchers use excess kurtosis to compare the kurtosis coefficient with that of a normal distribution. Sometimes we use this one to also to check the test for normality. All right, we have a positive kurtosis, we have negative, and we also have normal distribution. Okay, for example, we have a positive kurtosis, which is a degree of thickness is more. Degree of thickness is more. It's called Fe tail, or which has more outliers. The kurtosis value is greater than 0 at this point. And for negative kurtosis, we have degree of thickness is less. This is called short tail. We have few outliers. So kurtosis is less than 0 in this point. But under normal, it's called symmetrical, which means mean equal to median equal to mode. Kurtosis value is 0, so just like the skewness. All right. So when you look at this, this one is a box plot now. Before you go to box plot, you must understand that in kurtosis we do it because it's also a test. All right. It's also a test for the distribution. The main difference actually between skewness and kurtosis is that the skewness refers to the degree of symmetry, right? Whereas the kurtosis refers to the degree of presence of outliers. So you want to check outliers, kurtosis is the best to do that. So, but you want to look at the skewness. I mean, just look at the skewness diagrammatically. Okay, you can know, oh, this data is not normalized. It's not in a Gaussian distribution. You can see, but you may not be able to detect much of the outliers. But when you now look at the kurtosis, you can see, oh, outliers are there. You can detect outliers very easily. So there is a necessity to transform the skewed data to be close enough to a normal distribution. All right. So that's why we have to learn how to bring our data to Gaussian normal distribution. All right. So now we have what they call another one called box plot. Box plot, the shape of the box plot shows how the data is distributed, and it also shows any possibility of outliers as well, like the one we did in kurtosis now. So it shows that your data has is well distributed when the media is in this form, and if there's not outliers. So we have upper quarter, have lower quarter. Lower quarter is Q1, upper quarter is Q3. All right, so this is minimum here, this is maximum here. So 25%. The total from here to here, from Q1 to Q3 is 50%, 25. And we have another 25 here for this whisker. This whisker, the upper whisker, lower whisker. All right, 25%, 25%. So the total range now is called RRQ, which is called 50%. This RRQ is 50%. Okay, so take note of that. So I will explain further about that. So under the box plot, we have what they call negative skew, we have positive skew, we have no skew. So negative skew, it means that the median towards top of the data, this median now, you can see, when you look at it, this one, the median is the middle here, this median, this line is called median. But here, the median is towards top here, okay, which is on the positive side, towards top. Now, median greater than mean. So upper quartile is smaller than the lower quartile. The upper quartile is smaller than the lower quartile. That's what it means. Right? Upper quartile, this upper quartile is smaller. This one is smaller than lower quartile. So you can see that this place is smaller than lower quartile. So that's what it means. We call it negative skew. So the tail is now long here. Now we have no skew at all. The median is in the center of the data. It's in the middle here because symmetric. Median is equal to mean. Upper quartile is equal to lower quartile. This one is equal to this. This one is equal to this. Okay. And we also have positive skewed, which means to this side. The way we have in a skewness, we also have here in box plot. Okay. Median towards the bottom of data. Okay. And the median is less than mean. Upper quartile is larger than the lower quartile. All right. You can see here. Upper quartile is larger than lower quartile. You can see. So this is called box plot. Okay, it's very good to test our normality. We're going to see a sample later practically how we use box plot to test. Now, like I said before, the quarter range is in between here, which is called 50%, 25 this side, 25 this side. Right, when you measure from here down here, okay, I measure from here down here, anything you have between this line, between this whisker, maximum whisker, and the minimum whisker here, anything outside is called outliers. This is one, this is one, this is another one, two here also, outliers. All right, so take note of that. Outlier are data that are outside the range of normal distribution. They are outside the range. You know, many things can cause outlier in your data set actually. Okay, let me explain. I mean, conceptually, if data is collected, for example, now you want to collect data for a student or children age between age of 5 to 15, that is age of children you want to collect. So when you, as you are collecting data set, you are entering data, but at the point you now have age of 75, age of 80, in between the children age. That's not consistent data. It's not consistent with your data shape. So that is called outlier. So you can have many of them. So maybe you have 10 that is in that range. So you have 10 outliers. So the point will now be 10, maybe 3 year, 4 year, 5 or 6 year. So that is it's outside the range. The system will detect automatically that something is outside the range. It can smell some data integrity here, data integrity challenge here. All right. So there's a breach in data integrity already. So the system can perceive that. So it now gives you a form of outliers. So that means you can do something about that. Okay. We'll see how to handle that later as we journey in this course. So take note. So for example, now let's say we have a marital status, we have stress level, for example, under the box plot. Now this is marital status now, single, married, and divorced. We have stress level. All right, this is stress level. Okay, so we now plot the box plot here for each of them. This is single, this is married, this is divorced. All right, so we want to see their stress level. All right, so when you look at it, like this one, you can see this one how it look like. See this one how it look like. See this one how it look like. So this one is close to normal distribution now. Okay, very close. This can mean is close to center, very close to center. All right, but this one is what is a left now. This one is to the right. Okay, you can see that. So you can easily interpret this particular one. So we have a scale here. This is from 0 to, you can see from 0 here. Let's say from 0.00 here. Okay, and we have, let's say, 1 here, right? 1 or 100%, 1 here. So that's our scale here. So based on this scale, you can measure. Yeah, maybe we have a line here now drawn here. It'll be more easier to see, but at least with that, you can see what is happening around here. All right, and you can see what is happening. So when you look at it, you understand that the median of a single distribution is the lowest of the 3 distributions. Okay, because when you calculate the median is equal to 0.11. Look at the median here, 0.11. Okay, you can see median is 0.48, median is 0.88. One has highest median, the one followed by this. All right, so distribution of the distribution is positively skewed. You can see that it's positively skewed to this side. Okay, and it has 2 outliers here. You understand? So and because the whisker and half box are longer, are longer on the right side of the median than on the left side. That's why it is a positively skewed. Okay. The margin distribution is approximately symmetric. All right, it's symmetric because you can see the median seems to be in the center here. All right, this one is not towards the left. I mean towards the right. One towards the left is sometimes is in range. It's in a good range because both half boxes are almost the same length. Okay, almost the same length. 0.11 on the left side and 0.10 on the right side. So from here to be 0.11 here, 0.10 here. Okay, if you subtract this from here, you have 0.10. Okay, you want 0.11 from 0 downward, 0.11 here. All right. Then we go further. You can have that. So that is how it is skewed on this side. So it is most concentrated distribution because the interquartile range is 0.21. Interquartile range. What interquartile range here? From here to here, interquartile range. If you subtract 0.58 minus 0.37, you have 0.21. Is that correct? So that is called interquartile range. So you can calculate already from here to here. That is RIQ, interquartile range. IQR, interquartile range. So that is what you calculate. So you have 0.21. All right. So when you compare that to a single distribution here, or here, this one has 0.30. From here, you must this 0.32 minus 0.02 will give you 0.30. All right. So this one is have higher interquartile range. All right, that's it for single distribution now. And we also have a for divorce distribution. If you go to another divorce distribution here, you can see this one also is negatively skew here, or has left side. It has negative this thing, all right? Because this one is long to this side, right? And this one is also to this side. You can see that. And then when you calculate the interquartile range here, it is 0.26. You subtract 0.95 minus 0.69. All right, from here to here, we have 0.29, 26 rather, for the first this. So the median of the first distribution is the highest of the three distribution, because the median is what was 0.88. This median is 0.88 for the first 0.88. The one is 0.448, 0.01. You can see when you look at the scale here, 0.88 here. Look at scale here, 0.48, this 0.4, 0.48 here. Scale here, 0.11, this 0.2. You can see the scale on the scale. All right. So the default distribution is negatively skewed because the whisker and the half box are longer on the left side of the median than on the right side. Okay. All the three distributions include potential outliers. Okay. This outlier here, there are two here. There's one here. There are two here. Okay. You have outliers, all of them, even though this one only have one, which is because it's very close to normal distribution. We only have one, so one is okay. But this one we have two, don't have two. All right. So 50% of single has stress level. Okay, it means that 50% of single have stress level. 50%. Okay, so single 50% has stress level. Okay, that is this diagram. So it has stress level of 0.3. What does that mean? 50% means 50% means this from here to here is our interquartile range. Our interquartile range is 50% actually. Okay, from here to here is 50%. So the 50% has total of 0.3, because when you minus this from here, okay, don't forget that you have 0.3. Is that correct? So that is mean 50% of the single has what? It has a 0.3 interquartile range, 0.3 stress level. That's what it means. Now, if you come here now, this is also 50%. Okay, 50%. If you subtract this from here now, so what do you have? You have I mean, that is for married now. For married, it means married has stress level of 0.21. 50% of married has stress level of 0.21. And when you come to divorce here, from here to here, also, okay, so when you subtract it, you have 0.26. It also means 50% of 50% of divorce also have stress level of 0.26. These are stress level now. This is stress level. So stress level here is high. Okay, I mean stress level here is the one that you have highest stress level actually is when you subtract this from here, this one from here, from this 50% of this one has stress level of 0.26. 50% of this one has stress level of 0.21, while this one single have stress level of 0.3. All right. So the highest stress level is in the single. Single has highest stress level. You see that single has highest stress level, followed by the divorce, then the married. Married has minimum stress level, the smallest stress level. All right. So let's take a single distribution, for example. The interquartile range is Q3 minus Q1, okay, which we have calculated, okay, which we got our 0. This thing there, so 0.30 and the rest of them. According to the definition used by the function, okay, all values higher than Q3 plus 1.5 times Q3 minus Q1 equals to we are trying to look at outside the range now, which is our outliers, outside the right whisker indicated by the circle. So there are two potential outliers in a single distribution. All right. So and you can see that there are also one potential outlier in the married and two also in the divorce, like I said before. So this help visualize the 5 numbers summary, also useful for indicating whether a distribution is skewed or not, and whether there are potential unusual observation, which is called outliers. That is what a box plus what it does. You can see this is very easy to interpret. Okay, you can see that we have interpreted this just now, and this is why you are going to do your own data as well. We are going to interpret it like this also in your own analysis. Don't forget that. So this is called box plot. So we also have what they call QQ plot, right? Quantile plot, that's what it means. So it compares the theoretical quantiles that the data should have if they were perfectly normal with the quantiles of the measure values. All right, so this is called normal QQ plot now, for example. So when you look at it now, this is normally it should fall on the line. The observations, these are the observations, okay? These points are the observations. The data should fall on the line. If it's not, if it's normally distributed, it should fall on the line, okay? But you can see that this one is fall on the line, but at least it out some little bit out. This outlier, these outliers, there are not too many here. But compared with this guy, this one falls out of the line. You can see, okay? This one is close to normal distribution, close, but this one is not. So looking at this now, you know this one is totally far from normal distribution. All right, this is a called Q plot. So this is one you can use to quickly check as well, to check our normality, to test for normality if our data is normally distributed. So by plotting this, you can check, oh, this data is not normally distributed because it's outside the line. This one is okay. I mean, this one is not, this one is not completely out of the normal distribution. But this one is very close. Okay, this one is close. Okay, you can adjust a little bit more, and you can have a good distribution in this. Okay, so that is that for that for now. So we are going to go into practical to see what we are talking about from all this missing data transformation and outliers management using with the skewness, kurtosis, and box plot, normal QQ plot. We're going to look at how we can handle them practically and in our next session. Thank you so much for listening. I will see you in the next session.